is on analysis and design of precast concrete structures. I just want you to understand how the design is done. Again, I've kind of explained to you that different group come into play. I think during the break somebody asked me a question about, I think it's maybe specific to here, that precast structures don't go as fast as was envisioned to be, or a lot faster than cast in place construction. So one of the important things to realize is that with the precast construction, we talked about the different crews getting involved. Within each company, we take a precast fabricator. Within that company, you have different crews. Some do the foam work, some do the embedment elements, some do the rebar caging, some pour concrete. So they have a lot of people get involved. The logistic is a key piece, right? You have to get everything aligned. They don't necessarily do, they don't sit around and figure this out. There are softwares actually will provide you a lot of support in terms of what would be the critical path is. So the key would be to make sure that somebody on critical path doesn't get delayed, right? So the negative side to it, that if one group delay the construction, the cost would be pretty significant because they're delaying multiple other teams' time as well. So one thing I noticed in the US is that very focused on that logistical aspect when the construction gets started. If somebody is going to have delayed, they get penalized. If you're not producing product on time, you pay us money. So it's all in the contract, so that everybody jump hoops to make sure that that doesn't happen. So if you want to get this successful, then that has to happen. You need to make sure that the logistic is there, everybody play their part, so that the construction move according to the schedule. That's a key. I just want to touch, you know how to do the design of beams, columns, walls. If not, you're learning, or you're going to learn from other courses as well. But I want to touch on when you're involved with the precast concrete, how does the design get handled in terms of the actual design practice? So this is what I mentioned, that PCI has a handbook. So PCI is a Precast Pre-Stressed Concrete Institute in the US. They're based in Chicago. You have to pay membership to belong to the organization. So I don't know what the amount is. It's a pretty substantial amount, is what I know. They don't just take your money, they also certify you as a PCI certified precaster. So if you're a PCI certified precaster, in fact, they do that even internationally, but now they do it with international companies as well. Then they have expectation that you have to meet certain expectations from the industry. One is on the safety is a big thing. So each company has to keep track of how many days they have run the company without causing any injuries to workers, basically. That's a big thing. They have to have quality control. They have to do certain quality control requirements. They have to have certain capabilities in the plant. So all of that have to be met in order to be recognized as a PCI certified plant.
Canada has its own.
What's that?
Canada has its own.
They do have their own. It's a small entity, but they do have, yeah. So we have, as I said, I think in the PCI I belong to, I think at least 250 plus companies in the US are members. There are some international companies also participate because they, as a member, they get other benefits as well. So the handbook basically act as a primary reference for precast construction, precast design of structures basically. They don't act alone. So in the US, the International Building Code dictates that that's by law, you have to meet the requirements of International Building Code. So the IBC is the International Building Code. which tells you to go to AAC7 for the loads on the structure. So they will say the load should be combined in this fashion, but go to AAC7 to figure out what your loads are for your region or your structure or your location or whatnot. So let's say it's a concrete structures, then it's required from AAC7, once you design, the design has to comply with the ACI 318, which is the concrete design code. So PCI doesn't repeat, PCI handbook doesn't repeat any of those information. But once you have the structure, PCI handbook guides you with how to design, how to integrate the precast component into your design as well as the construction. So it's another layer that comes in, which is something I want you to understand. I know I'm supposed to talk preliminary design today. I'm going to delay to, because I want to introduce the handbook a little bit. So, because the handbook gives you a lot of information, at least I can get an older version electronically and I'll share it with you. And that way you know what typically is there. If you're interested, you can become a member or get a more recent copy. I think anybody can purchase a copy if you want. But for the purpose of this class, I don't think we need a new version of it. So the designs are done at the member level because the loads has to be figured out at the member level, because precast components are basically, each of the members are what they're going to be producing. But at the end of the day, or the necessary check has to be done at the structure level, right? The structure is the one has to take the load. Once a design is completed and constructed, then it becomes a structural problem. So the structure has to, so when I say structure, that includes the connections and their performance as well. Typically in precast, pre-stressed concrete, the serviceability governs the design, not strength. So if you know the service level load, basically you have your product because the handbook standardizes the components for you automatically. I think I will continue to emphasize that connections are critical, that we will talk about the different type of connection that gets used in precast. So if you have a structure that you're going to be relying on precast elements, then they kind of use these languages as bearing wall systems. So basically the walls are responsible for resisting loads. So if we have lateral load, heavy lateral load, either due to wind or earthquake, the bearing walls can be used more effectively. So the bearing walls typically refer to carrying the vertical loads. They can carry lot larger loads than individual columns. You could choose a frame system if you need to have opening on the structure. Sometimes wall structures are not ideal. So in that case, you may choose to have a frame system. The term shear wall gets used often when they are used to resist large seismic loads. So when they say precast wall is going to be used as a shear wall, basically implies that they are the primary load resisting systems for earthquake loads. And they're typically integrated into the core of the structure. They may have some walls in the perimeter as well. The dual system is combining walls and frame together. That's what the dual system referred to. It's not uncommon to see walls resisting load in one direction and frame direction load in the other direction. And that comes in because front facing of the building may require more opening because they want to have those spaces allocated for commercial purposes. So it's possible that they may choose to have this combination of both walls and a floor, so that becomes a dual system. The floor and roof diaphragms are where they use double T's or hollow core planks. Hopefully some of the industry folks will show the operation of how they do double T's. I think you've seen a picture of double T already. The hollow cores are pretty efficient. construction method for floor slabs. They're cheap, they have cavities in the middle, which makes it more attractive. It can be used as lighter weight elements, and so it has its own benefits as well. So the material properties, I want you to understand. So precasters tend to use higher strength materials because its advantages. As you learn more and more about pre-stressed concrete, you will appreciate the higher the material strength, the better it would be. You can make the elements lighter. In cast and place concrete, I think we still use in the US 30 megapascal concrete. But precasters typically will produce somewhere in the order of 50, 60 megapascal using just regular concrete. Because they have mastered the mix, so when they release the strand, so one of the things with the precasters is that I talked about 24-hour cycle. So if there are pre-stressing involved, the load has to be transferred to the concrete within 24 hours. And the 24-hour, whether you can transfer the load or not, depends on how strong the concrete is. So the higher the strength, the most likely that you will achieve that. So for that reason, they tend to use, it's not uncommon to see even 60, 70 megapascal within concrete for precast products. If you want to have higher strength, they could easily produce, they could go up to 100 megapascal without much difficulty. So if any reason you want a higher strength concrete, you talk to a precaster, they will be able to accommodate that. Pre-stressing strand is heavily used either for pre-tensioning purposes or sometimes pre-tensioning is done to improve construction. So if they figured that you have a long span beam, that during transportation the beam may see tensile stresses, could potentially crack, they could include some temporary pre-stressing into it, which they can cut it later on. So they do creative things like that too. It's not a big challenging operation to make sure. So that's what you want to have, the interaction with the precaster, so that you analyze the beam, not just for the structure, but also as to how it's going to be transported. The reinforcing steel is typically 415 megapascal onwards. They're starting to use higher strength steel, but not frequently though, I must say. I think in India they're using more and more.
Now high strength steel is picking
up, yeah. So anytime you have higher strength steel that you can incorporate it, it cuts down the congestion of reinforcing steel, right? So as long as you meet minimum spacing requirement and things like that, you would be able to use higher strength. So precasters typically prefer to use higher strength materials. The loads and load combinations, again, whatever the specific code in the US is the AC7, would dictate what loads and load combinations should be considered for a given structure. So one of the unique things you see here is the construction load, which you don't normally see. The construction load has to be integrated because it has to be assembled. As I said, AC7 provide the load combinations, and then on top of that, whoever is erecting the building will come up with some load cases because of the sequence they choose. And if that sequence doesn't look good, they can change the sequence. So all of that has to be done in advance because that drives the logistic for the project as well. The design process for individual member is not something that you will go through in greater details because the handbook provides you a lot of guidance. So we talked about the fact that service load typically governs the design, but you still have to check the strength limit state. Often precast combined with pre-stressing is designed to remain crack-free. But if the cracking takes place, then the stiffness can change significantly. And so that's something you need to account for in the design. So if you design it to be crack-free, then you have to make sure all the way to the assembly, the member remains crack-free. It's not ideal to allow pre-stress member to experience flexural cracking like the regular reinforced concrete. I think the reinforced concrete can, they crack under service load conditions. Cracking will induce corrosion, water ingression, and then corrosion. So in pre-stress or precast pre-stress members, the pre-stressing play a key role. They basically keep pieces together. So if you cause corrosion to the pre-stressing street, the consequence would be much more severe compared to reinforced concrete. So it's often designed to be crack-free. One of the advantages with pre-stressed concrete is that, or precast pre-stressed concrete is that, if you want to have a floor slab for a dead and live load, it's going to have some kind of a deflection. You can apply pre-stressing and create a upward deflection due to pre-stressing. By the time the load comes in, it goes back to almost zero deflection. So that helps you to keep the floor slab crack-free, for example. So it's not a difficult thing to do, but you don't want to crack the slab when you ship it or anything like that. So it has to be looked at. Casting it, I think I probably used the term handling it, which is how do you pick up the thing and store it? Would you pick it from two ends? If you pick it from two ends, will it cause cracking? So in those cases, they may have a spreader beam and pick up the slab using 4 points. So those things have to be looked at. You don't want to cause any cracking at all. And then it has to be stored, and then you have to pick the component in the same way when you transport to the site. And then whoever is working on the site, which is a different crew, needs to know they have to pick from 4 points, not from two points for that particular member. So all of that has to be communicated all the way so that structure remains crack-free. It's not, again, difficult, but it has to be done. On the shear torsion side, I think one of the unique thing is you will learn web shear, flexure shear kind of cracking in terms of how that influences depending on pre-stressing. The punching shear is a unique feature comes into play because typically floor slabs are supported on corbels, for example, can cause punching shear failure, and that's something given special consideration. There's a lot of work has been done in terms of how it should be detailed and connected. PCI detailing guidance provides some knowledge in terms of how they should be designed as well. I think some of the aspects what I mentioned here, effective pre-stress losses, stress limits, those things Professor Amalan probably covered yesterday. You will learn that in your pre-stress class if you haven't done it yet. The serviceability check, the usual serviceability check should be done, like deflection controls and crack controls. But one of the unique thing with the precast concrete is that the vibration can become a problem. So you need to do special analysis to make sure that vibration is not going to be an issue. The vibration comes in for two reasons. One is the members are maybe not well connected, so your members is not as what you envision. But the precast members, because of the high strength material, tend to be thinner and lightweight, unlike the cast in place. So they will be prone to more vibration issues. And same applies to UHPC now. They're getting even thinner. In fact, in some cases, people worry about even buckling of UHPC member because they are very thin elements subjected to fairly large compressive forces. So again, it's all specific to those materials. There are things that we should take advantage, but there's also some challenges come with that. You have to pay attention to it as well.
What is the acceptable level of vibrations that usually?
I think typically the vibration issues doesn't come into play unless occupants complain. So I think they may use some numbers, but like you can work on structures, like parking structures, you can feel the vibration. As long as it's not a comfort issue for occupants, it's not given. So I don't know if the code specify any testing, or I don't believe they do specify. But I think the handbook provides some guidance in terms of the length and thickness, cross-sectional area. So that when you're supporting, they eliminate those issues as well.
It's particularly, as you said, now we're also doing some work on ultra high performance concrete-based outdoor elements. When you enter 200 meters, it's a 20 meters. With 250 mm slab, the
exactly.
will actually control more than anything else.
Yeah, so it's an issue. Okay, so I think as we go through, I'll show you some aspects of how hollow slabs are designed or detailed. The double T's. So these are typical elements. Precasters will make them day in and day out. Precasters also know what size elements get sold frequently. So I talked about the fact that they will have a crew working 24-hour cycle, but sometimes they don't get any projects. If they don't get any project, they know they can sell this particular pile, for example. So they will actually produce them and keep it in the yard. They don't idle their crew. So they will continue to produce standard members, which they think is easy to sell or has higher demand. There is actually a very separate industry in the US. I think they are much bigger in terms of how much revenue they generate, as well as the number of companies present in the country. Is number of precasters are focused on like casting culverts, pipes. The expectations are pretty low in terms of what they have to meet, and they have a specialized, and they don't actually produce anything else because they make really a lot of money on those products. The culverts of different sizes, pipes, storage structures, storm shelters. The hundreds of companies actually make and make good money out of it. In fact, the structural guys make less money compared to those guys. And they don't actually belong to the PCI. They have this separate organization in the US, and they have their guidance and things like that. That's also a good market for growth. I don't know if it's popular or it's common here in India.
Which pipes are there?
Pipe is there. Okay.
There is a company called Cube.
Oh, okay, Cube. Yeah.
It's there for a long time from the British period.
Yeah. He was a. Yeah. Okay. Yeah. No.
Cube.
Yeah, they've done like railway ties made out of precast. In
India also, those like the railway sweepers, they come under the specification of the Indian Railways.
Oh, okay.
They are covered in the building code.
Oh, okay. On the connection side, we will talk about the gravity connection, lateral force resisting connections, and emulative versus non-emulative connection. So gravity connection is basically you make sure that you have the established sufficient connection for a gravity load path, right? So the load has to go from the top of the structure all the way down to the foundation. The lateral force resisting connections have to make sure any lateral load, which is the most critical connection when it comes to earthquake, wind, type of load, the structure can handle those. So connections play a role. So connection that you use for vertical is not going to be viable for lateral load resisting elements. So resisting lateral loads. So they will have specialized type of connection. We talked about emulative concept. So this is emulative term comes in because you are creating connections to make sure your precast structure is going to behave like a cast in place. That's where the term emulation come in. So you're emulating your precast structure to behave like a cast in place construction. I shared one paper, it was written by one of the PCI committee member, I believe. I just want you to have some material on emulative details as to what people come up with. Typically, these documents are published either through PCI or ACI. ACI has been handling these things, so this particular document refers to, it's a conference paper, but it's pretty detailed, refers back to an ACA document, which is actually going through revisions right now. So again, if you happen to go into that direction, you need to find the latest and greatest and get into it. But to gain knowledge, you don't have to spend money or anything. You can just rely on this to understand what emulation is. So emulative connection, people have come with different ideas. We'll go through them. So the non-emulative connection concept is to take advantage of the precast product features and design connections so that it doesn't really try to behave like regular concrete. There's a lot of work has been done in the last 20 years or so on the seismic related details. But several of those connections can be also simplified and used for non-seismic cases. But I think in India, seismic is also becoming more and more important piece. So looking at both sides is actually well worth it. Another country that uses precast quite a bit is New Zealand. New Zealand uses a lot of precast because of some of the research, well-known researchers establish research and make recommendations. They all came out of University of Canterbury in a city called Christchurch. So they built that city with a lot of precast concrete structures. In 2010 and 2011, Christchurch experienced a fairly large earthquakes. A lot of the building got actually damaged. So there was a lot of things people learned. They did go through some damage. So some lessons that we learned. Some of the emulative concept didn't work as well as we thought it should work. It becomes more obvious now. So since then, there have been a lot of work done as well. But in Christchurch, one of the other problem was that the way insurance played into that, how the buildings were protected, played into whether they keep the structure or take the structures down. So most owners felt that taking the structure down gave them a better insurance outcome. So 90% of the city was actually, basically demolished, and then they rebuilt the city. So it's just not the engineering playing a part. In this case, insurance industry played a part in terms of whether the structure should be repaired or should be kept in place. One of the most challenging with the precast structures is how you work your flow system into it, right? The flow system is a challenging piece because again you're integrating or building this from pieces, but they have to act as a continuous, what they call a diaphragm, so that they should transfer the load across. Often precast diaphragm gets questioned in terms of how they would accommodate some of the displacements that columns and beams go through. But if you look at cast in place world, the demand are the same. So, but when they go through approval process, if it's precast, they flag it, not necessarily cast in place. Again, work has been done in this space, typically to make sure that the terms that you'll see here, core and collector forces, it depends on how the force gets transferred from. So if you take a seismic, you get the inertia force created on the floors because of their weight that has to be transferred from the slab to the frames or walls supporting the structure. And whether you collect the forces and transfer them, or you act as a cord, which basically has a strut to transfer the forces, it all depends on how you conceptualize this. If you look at the research in this space, there's a lot of work has been done, but I don't believe that we figured out everything. So youngsters, if you want to go master's, PhD, there's still a lot of work to be done. So you could certainly get into these research areas because it's an area that people make assumptions, they do research, but often it's very confined to that particular space. I would think that even the ACI still revising how diaphragm should be designed in cast in place versus precast as well. Topping slab is, so you see in the picture where I had hollow core plank. So in some design requirements, they ask that if you put them as elements, precast elements, at the end you should have a topping slab, or with thin slab, cast in place, cover the entire region to integrate together. Some argue it's not needed. Typically, so parking garages don't use topping slab. If it's a residential structures, commercial building, they would require, code will require you have to have a topping slab. We've done some research to show that you don't really need it. So I'll share some of those things. Again, it's what I present to you is not out of Bible, just everything is correct. It's just what's out there, you need to learn and explore and see where this is going. I'll spend some seismic design related topics. Basically, what precast industry has done over the last 20-25 years is they develop specialized ductile connections promoting the fact that precast has its unique features and we should take advantage. If you have gone into the seismic design world, the capacity design philosophy is what gets used for cast in place or steel structures. The same applies to precast structures as well. We have also developed a number of special systems for precast structures. In fact, some of them have been so successful that timber industry has adopted it with post-tensioning in timber elements. Steel structures have adopted it because the precast has successfully shown you can do this. The analysis, I think you now realize that it has to go into erection and construction steps as well. You have to decide, again, it's not the designer's responsibility, but erector has to decide temporary bracing. Where do they go? How do you support pieces? Will they be stable? So the stability during erection should be looked at. And then load path prior to completion. So I talked about the fact that all of the grouting, welding takes place after you assemble the entire structure. That's a typical process because the different crews get involved. And also, as you keep building, the building also settles because of the gravity loads and things like that. So they want to allow all of that to take place before they do the grouting or welding requirements. But then, if you have a cyclone happen to come by, you don't want to lose the structure. So there are requirements to make sure there's this clear load path. If the structure is temporarily supported, it can still survive some small level of earthquakes or wind load so that you don't lose the structure. Let me see. Okay, I'll go through this. And how are we doing with time? What have we have next break?
You can take another half an hour if you wish.
Okay, time is there. Okay, good. Durability and fire design. So the precast world has done a lot of investment in terms of making sure that they provide fire protection. Again, they compete with not just cast in place, but they typically compete with the steel industry. So they want to produce structures that will provide better fire protection as well as environmental effects. So if it's happened to be in close to a shore, for example, if you have a steel structure, you run into a corrosion problem. And here they will figure out the better cover requirements and make sure. So if you can provide adequate cover, and as well as if you can keep the structure under compression because of pre-stressing, then the cracks won't develop. So definitely both of them advantage in an environment that can be exposing the structure to salt water, for example. From a design system, a workflow point of view, it's important that first you select a system. So this system is a designer select the system. So you say, I'm going to use core wall structure. So that means wall is going to be a primary element in terms of resisting loads. So that's something you decide. At that point, if you decide that it's going to be precast, you need to bring a precaster into your team. Either, I think I told you, it could be an integral part of your team, or you have a subcontractor who will be interested in building the structure. Then you design members. You first basically go through a preliminary design, which I will talk about it. And then you will do connection design, right? We talked about connection. So connection design needs to happen. And then the system level verification is the most important thing. You design members, but at the end of the day, the system has to tackle the load coming in. So let me just summarize this, and I will spend a little bit of time on the PCI handbook. So basically, what I covered on the design side is that if you're going to use a precast structure, the PCI handbook will be a handy piece to have, because PCI handbook will dictate what type of elements, what type of design, what type of connections that you need to come up with. Emphasize that connections basically govern the performance. The connection has to be robust in order for the structure to be performing well. Serviceability often controls the design, right? In the pre-stress world, you should know that serviceability governs the design. And then system behavior must be verified. So if you have structure that has, eventually the structure is the one that's going to be subjected to the load, they have to perform in terms of displacement requirements or vibration or whatnot. You have to meet those requirements. Any questions?
Are there any fire-related issues that have been reported from the past? Because the moment you go for precast systems with high-strength concrete, your thermal mass comes down.
Yeah. So PCI has actually done quite a bit of work in the recent days. I don't know if it's in the new handbook or not. I need to look into that. So two areas they worked on. One is fire resistance and the other is blast. Both of them, so the way it works, I think is most organizations is that they will assemble a committee. The committee will work on state-of-the-art document, guidance, whatnot. They will come together. They could also make recommendation for PCI to complete some research if they see a gap. Committee will then put out some design guidance on that specific topic. Then eventually that comes into, so I mean, I work on some pilot stuff for PCI. I think it was maybe we completed the study maybe 11 years ago, I would say. So they took that. Initially it was just a recommendation from the committee. Now they integrated into ACI, IBC. PCI put out a handbook on the pile design, and then now they're working on ASHTO. So it's like 11 years later, right? So it's a long process by the time they get into but they will take it to the right body. So they did some work on diaphragm. It's integrated into the ACI code. It's a long process, but they do have some recommendation for fire ratings is what they come up with. So depending on what you're asking, but I think they have included. Let me see if I have this in the current version.
The reason is why now with high-strength concrete, performance is very poor.
Yeah.
I mean, with UHPC again, we go for more thinner and thinner systems.
Yes. I mean, UHPC has completely different, other problem also, right? So, let me change the display setting. is this not showing up? I think this is what we had trouble earlier. Handbook. This is an older version. I believe it's the 6th edition. It was published probably, I think you'll see, it's 2004. Is it 2004? Is that what it says?
Yeah.
Yeah, so it's an older version, but they update the document every 5-6 years. The 9th edition just came out. Basically, they update the chapter. I think for the interest of this course, I want to check and see if this is available as a PDF. Then I'll share it with him, and he can.
I think it should be there this year. I think we have it, right? We have 7th or 8th.
Yeah, but I think they put a lot of restriction in terms of sharing. But I think they released this one, but I'll check and at least send this file to you. You can give it to them. So if you going to go in that space, if it's needed, then you can purchase, so you can find a copy, I suppose. But what I wanted to focus is on the content of this for the time being, and then we can use this a bit more later. I could barely read. Okay, this is might be much easier. Okay, so you could see the handbook has, the chapter 1 is on precast pre-stressed concrete. So it's basically some general information like what I covered earlier. Then they have a preliminary design of precast pre-stressed concrete structures. Then, so they go through 2 steps. I think we use conceptual design, which is basically what they call the preliminary design. And then you do an analysis and design of precast pre-stressed members. Then you do a design of precast pre-stressed concrete components. So this way you design each and every element. The next topic is product handling and erection. So as I said, the handling comes in because of how you would handle the completed product within the plant, transportation, as well as during erection. So that's on the next chapter. Design of connections is on the chapter 6. The architectural precast concrete is actually now has a separate document. I'll find and share with you, at least show it to you what that looks like. Let's see, design of connections, and then selected topics for architectural precast concrete, tolerances for precast. So that's something that I haven't talked much. Industry has a standard for how much tolerance. So that means if you cast a member, it has to be within plus minus some dimension, right? That's a industry standard. So if you are within that tolerance, there won't be any penalty. But if you come short, then there's a penalty for it. So sometimes they can reject the member because member did not meet the tolerance requirements. Thermal, acoustic, fire, and so there's some information there on the fire as well that Professor Surya Prakash was asking, as well as other consideration, specification and structural practices, and general design information in chapter 11. So that's basically what the handbook gives you. Let me see. We go to chapter 2, which is where the preliminary design is discussed. Yeah, this is another pretty thick document, if you like. So the preliminary design basically talks about frame dimensions, span to depth ratios, connection concept. So under preliminary design, you figure out some of the dimensions for the framing. The span to depth ratio comes into play in terms of deciding how long, how thick or how deep your member is going to be. So if you're designing beams, the longer the beam, the deeper the section is going to be. And so those are standardized as much as possible so that everybody uses, so if you say the number is 1 to 15, then that's the range that one should expect. So they're providing you a lot of information to guide you with the design. Connection, at least conceptually, you had to decide what type of connection you're going to be using. And so that's what the next topic is, gravity and lateral load resisting system. So this is what is your vertical load path and what is the horizontal load resisting system. So those things have to be decided at the preliminary design level. And then mechanism for the control of volume change. So volume change accounts for basically the thermal expansion, creep and shrinkage effects. Everything is covered into that topic. The next section is on explanation of load tables. So basically, you may have some superimposed load. As I said, if you have a flow slab transfer to the site, you're going to put in-situ topping at the site. That's where the superimposed load comes in. Various other design parameters. So pre-stress loss. So these things are all talked about. But if you go back to, it's kind of a, so if I go back to, I don't know if I can go back to, what chapter is that? 2. Yeah, chapter 4. Let me see if I can look at chapter 4. I just wanted to show you one of the chapters which has components in it.
That's all.
And structures. This is not the right one. Let's see. So this chapter 3 analysis basically what I talked about today, where they talk about different loads and what code and requirements you have to comply with. So this is IBC code is, but the International Building Code is ASC 7 define the loads and load combinations. These two, the NEHAB 2000 and NFPAs, in some areas or some regions, they may be adopting these instead of IBC. The NEHAB provision basically eventually goes into IBC. So if you want to follow what the upcoming changes are, you can possibly use the NEHAB provisions. NFPA is another organization. They put out a design code. Again, for political reasons actually, that they couldn't agree with each other and they published their own code. If a region chose to use it, then they had to do accordingly. These ones talk about the dead life, snow loads. The setup is kind of tricky to go through the material. I'll figure out how I can do that. I want to show you one preliminary design of precast concrete structures. So maybe chapter 2 is where they talk about, I think. Or it's easier. Let me just pull this here so I can see. Okay, so these sections, the 2.4, 2.5, 2.6 onwards, they talk about how you will do the preliminary design. So that's what I wanted to show you. 2.4 is. So this is a double T floor. So so you have a building that you're designing, so let's say a parking garage. So you have dimensions for each of the bay or how you're going to be supporting the floor slab. So what they provide here is the span for a given span based on the strand pattern. You can pick and choose which double T is going to work for you. So if your span, if it is 50, then you have a choice to pick any of these double T's depending on the cost of this element that you're looking at. So you don't have to actually do the design when you do an initial preliminary or conceptual design. So you will pick this structural element and then you will check to make sure that for your load, this is going to be sufficient. So if you pick, so this is what they are changing here is this number of strands. So this has 68, 88, 108. So that's as you go down, the cost is going to go up. Typically based on the type of structures that you design, you should have a feel for, from the experience, maybe one of these is going to work for you. Then you pick that and that will be your double T that you're going to be using for the floor. And then for the specific load that you are dealing with, then you need to check and make sure that slab will remain crack-free for the dead, live, and any other loads that you're using. So you don't quite do any design from the scratch. If you're going to do double T, you don't design double T. You pick a double T from here. Now, but for the precaster, they have set up to produce all of these fairly easily with the steel formwork. So if you tell them you need 54 feet span with 68 strands, you need 20 of them, they will just produce them for you. And formwork is already there, they can produce them, you know, so these double T beds are not just they produce one, they could be like, you know, 50, 75, 100 meter long, and they can block and cast them. So they may produce 5 double Ts a day, and every double T will look the same because it's used the same strand pattern, same concrete, so they make sure the quality is maintained. Same thing applies to, let me go back to, so we looked at double T, I don't know what that is, I can't barely see anything from here. So this is a hollow core slab, so this is the hollow sections. This is a 4 foot wide, so it's about 1.3 meters. This is 8 inches deep, so it's 200 millimeters. Then you come here and you decide what span length that you're looking at and how many strands that you would need. So once you pick a product and tell precaster, that's what I need, then they know how to make that. And they have done it before. They can make adjustments. They will get the bed ready for you, and off they go. So you don't need to go back and forth in terms of figuring out, okay, what hollow core slab to. Your job is as a designer to make sure that slab works for you, or whether you need to change the dimension of the slab, or you need to go a different size or whatnot. So that concept goes all the way to beams, columns, piles. So any of these products doesn't get into, let me see, what is this? Load, so that's stem deck members. So 2.6 is beams. And you will also realize that by picking the standardized product, the cost will also be pretty competitive. So if you go and ask them, oh, can I do this, make it a little longer or maybe a little wider, then they have to make specialized formwork and the cost is going to be increasing as well. So here's a simple rectangular beam. They give you all of the properties like what the steel table gives you. They have a designation, so you can refer this in your design. And then these are the design elements. So if it's a span of 34 feet, this particular number of 58 strand is not going to work for you. You're probably going to cracking or whatnot, so you need to go to something here, or you go deeper for something else. So it's like picking things from a catalog. I think if you've done assembled IKEA furniture, it's kind of like that, but you have to pick the elements that comes together, right? So the handbook is handbook, what it has done is standardize the industry across the country. I don't, like Satyasilan said, none of that has happened here.
In India, some major companies, they have their own catalog.
Yeah.
Maybe small number of products,
But
they
yeah.
have got their catalogs and they use.
Oh, I see.
But
There is no unification.
unification is not there. We need a countrywide document.
Yeah, and I think given the country size and the growth in infrastructure, it makes perfect sense to have something like so. If I've seen situations where a parking garage is being built, they identified what their specification, the ID for the double T is. If one precaster is not able to produce all of them, all they have to say is, "Can you give me this double T? 10 of them. I'll buy it from you." Right? So they can produce, they will ship it from different locations and it will arrive at the site they assemble. So it's everybody benefits from it. So the standardization is the main piece that why the industry has been successful in the US. And they can complement each other. Like when you see the catalog, some of them only do one particular element, as I said before, right? So whoever works on hollow core may not work on piles or columns, and there will be another precast that comes in. So everybody benefits from that exercise. If you, let's see, go back to, there should be standardized for the piles as well, piles and so the next one, yeah, so this is wall panels and that's piles. So they have done enough to figure out that these products don't have to be, what is this? Okay, this is a pre-stressed columns. So for the columns, if you look at it, so they give you the moment load curve for each and every column that they standardize. So everybody uses the same cover concrete. So here are different column sizes. So again, you have to pick what column that you want to use for your particular project is. So otherwise, somebody is checking this every time. If you don't standardize it, you check, then you have to come up with the formwork, then you build them. So quality is not necessarily you're improving it.
I'm just curious. See, for seismic design, we require 125-degree hooks. But these columns are not having 125 degree. Then, if you are using precast members in a seismic region, how to handle the situation?
Yeah. So that's also goes back to what I said earlier, right? Because we keep thinking like cast in place, detail has to work here, right? So like with precast, we move more towards rocking, and they don't seem to have any spalling, so hook doesn't really matter what shape you have, right? So we do put some additional requirements on rocking structures. That's on top of this. It's not that they will not change the details. So you could take this detail and say, I want this column, but I want confinement added to the bottom with the 135 hook. They will do it. But what they don't like is changing the dimension, because then you don't have the formwork, right? Yeah, this is something that you should go through, and again, I'll check and I'll share what I can share with, where's the pile? Pile is the last topic I thought. This pile, it's not even focused from here. Yeah, so these are typical piles. So this is obviously a square piles. They produce square piles with, it's a hollow square pile with a circular arrangement for the strands. So there's no other reinforcement, it's just a strand, no regular reinforcement. This is more efficient, so they produce octagonal piles. Pretty often it's get used in the seismic region. This is round piles. Round piles, they can also do what they call a spun casting. So they basically, spin the formwork and get the concrete, create the hollow sections. And you come down, it's the same details. They provide properties, and you can pick for, depending on the file type you're looking at, you know what the properties are, you can design based on that. So it's almost like how the steel industry operates, right? I mean, steel industry is all standardized. And that's one reason that they have been successful. They don't wait for somebody to ask for a steel section. They're readily available. Everybody makes them to a standard size. Everybody is forced to do it. So this is pretty much what concrete industry, precast industry has done in the US at least.
I have a question related to precast. Why is still using a PS system and the entire world is trying to
So I think it's about, I don't know, I'm going back. So about, I think maybe 15 years or so ago, US decided to go back to, adopt SI units. But what they did was they were trying to design everything in square, inches and feet, and then convert it in millimeter and meters. And the formwork and like the construction industry just had a tough time trying to adjust. Basically, they are building everything to the feet, but it's written in millimeter. And at that point, they decided, it's okay, we'll just go back. And then they gave up on that. It was a very short period of time they tried to do it. But so US still adopts the imperial system, basically.
It's like, say, sometimes in India we think, why can't we drive on the right side? You can't change.
Yeah.
Rest of the world drive on the right side, but only the commonwealth countries drive on the left side. But we can't change.
At the moment we see SA books and it's little difficult.
They won't change because that's the practice.
Conversions.
It has become a religion. They won't change.
Yeah, but if you look at Canada, for example, so they adopt a lot of things from the US. They convert, they create their own, they make adjustments. So it's not impossible. Now, Canada is a relatively smaller country, so they're able to do it. Any other questions, comments, concerns? Too fast? Am I going too fast? Too detailed? You want less detail?
I was asking Professor in the tea break also, like you mentioned earlier, like whenever the erection point of view or construction point of view, the panel which is in precast in the workshop, when it is to be transferred to the site, so is it any specific sequential manner it is to be lifted, like 4 point, things are 2 points, so that the dead load on the panel is not going to change its behavior?
Yeah, absolutely. So I think the handbook also provides some guidance in terms of, given the size, how it should be lifted. So that is actually decided when the shop drawing is created. Because even when they lift the member out of the formwork, they decide at how many points they had to lift. So they put a lifting hook inside. Lifting hook is typically a bent strand piece, right? They put it inside. So whether they do it 2 points, 4 points, so they decide before even casting it. So once the casting is done, that's how they will handle the lifting, transporting, loading it on the truck, unloading it, everything has to be done in that manner. They label everything, it has to be a 4-point pickup or 2-point pickup, and everybody has to follow. If somebody violates and beam, cracks, then it's their responsibility. Any other questions? So I'll stop here, Surya,
Yeah, we can.
and then break, and then,
Yeah, we can stop here, I think.
okay.